Happy curly caramel.
Not that bit, CJ. CJ. Yes, but you know the banging sound that you're making is loud. Okay. Do you guys have your textbook ready?
Yes.
Mr. Andrew, it's not time yet. Why you started?
Do you guys have your textbooks?
Yeah.
Okay. All right. Could I get you to find in chapter 33 the charge of an electron?
Could you repeat what you said, Mr. Andrew?
Oh, type it up. So
Mr.
it'll pop up in chat. What is
Okay.
the charge of an electron? Where in chapter 33 of Hewitt?
Do you mean by like negative charge, like that?
No, the amount. So
Oh, okay.
you learned did you learn last chapter that charge is measured in coulombs? Yeah, it's also in chapter 32, but I'd like to see if you can find it in chapter 33. Anybody found it? I'll give you one hint. The charge of an electron is the opposite to a charge of a proton. If you can find the charge of a proton, you can figure out the charge of the electron. I think only a charge of a proton is mentioned.
What are we talking about?
So you have the textbook, Dylan. I want you to open chapter 33, look through chapter 33, and find where, and then tell me how much is the charge in one electron.
Can I not just look it up?
Online?
Yes.
Sure, you can look it up online, but then you need to tell me how you figured that out from the textbook.
Okay then. Wait, chapter 33, right?
It's in chapter 33. It doesn't state directly. It states it also in chapter 32, but in chapter 33, it states the charge of a proton. And if you know the charge of an electron is equal and opposite, you can work out the charge of an electron.
So if the proton's 0, then the electron's 0.
No. So one of the reasons why we have the letter Q for charge instead of C for charge is because Q stands for quantity or quanta. And you get a lot of your advanced physics or quantum mechanics from this concept that there is a set amount of charge for one electron. There is a set amount of charge for one proton. Because these are discrete numbers, it is a fundamental unit. That means one electron will always have this amount of charge. One proton will always have this amount of charge. Has anybody gotten close?
I think I know what page, but I don't
Closest
find.
thing I found was electrical potential energy is. Uh, Never mind.
What page was that?
524.
Ooh, close.
Ooh.
What did you have, Dylan?
Nothing close. Not yet.
I'll narrow you down to page 525.
Did Yoram got it correct?
That's correct. Where did you find that, Yoram?
525.
Oh, it's right there in 525.
There we go. On page 525, it states that the charge in a proton is 1.6 times 10 to the negative 19 coulombs. So when you see an equation that has a Q in it, that's talking about the amount of charge that the whole object has. However, if we are looking at discrete numbers and you have an electron, one electron will have that exact number of coulombs. How many electrons would you need to have 1 coulomb of charge?
One?
How
Is
many,
it?
how many electrons do you need to have 1 coulomb of charge?
More than one.
Can I have it to within 3 significant figures?
Billions.
Sorry?
Millions.
Millions isn't enough.
Billions.
Billions isn't enough. Aduh.
Quadrillions.
Okay. So if you have,
Quintillion? Is it the one that starts with a G?
okay, so if you have 1.6
Gigallion.
and you want to get that to 1 coulomb, actually, what am I doing on here?
Oh, I remember you told us this. It was this really, really long one.
How about we do it in the calculator function instead?
It's like 0.0000.
So yeah, okay, I'm going to share the calculator screen here. So if you had 1.6, and it's not, this is difficult to do. So it's to the power of negative 19, negative 0. So negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. That's the number of coulombs you have. So you want to get that into 1. So 1, and you want to divide that by the answer. How do I get answer on this?
Is it
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and then it's the minus. So then you got to minus 19. So it's an enormous number, and every zero. So you've got 1,000, million, billion, trillion, quadrillion, 6.2 quintillion. You need 6.2 quintillion electrons to get 1 coulomb of charge. That's
Is that a lot?
It's a whole lot.
I mean, can it kill a human? It looks like it could.
I think so. You'd probably be able to do that. I'm not sure. So Let's find out, actually. I'm curious now.
But it is compared to volts. Is it like
Volts is different. Volts is different. So we'll get to volts in a bit, but I don't really want to get into volts yet until you get this concept down pat, that there are distinct quantized charges on electrons. So let's have how many coulombs
countries recognize
is
monopoly?
in a lightning bolt? How many coulombs in a lightning bolt? There are 15 coulombs in a lightning bolt. Oh my goodness, that is
Dang.
terrifying.
I mean, you could survive it.
Yeah, but even 1/15 of a lightning bolt isn't going to be happy.
Yeah, any part of a lightning bolt isn't going to be happy, Mr. Hendro.
How many coulombs in a Van der Graaf bolt? Van der Graaf it doesn't say.
I think it's not even one. It's megavolts. Well, look at that.
Can we figure it out?
I don't want to.
I've been zapped by one before. There should be an equation that allows you to figure it out. So if you look, so Van der Graafs are dependent on the size of the sphere. So a 1 meter sphere will have 3 million volts. How can we work out the amount of charge in 3 million volts? Is there actually a reference? There may not be a direct connection. Okay. So the way you think about volts is the amount of energy for every unit of charge that you have to get that unit of charge to move. So if you have 100 volts, that means you need 100 joules to move 1 coulomb of charge. Does that make sense?
A bit.
That's your relationship there. But I'm not really. Oh wait, Becky's trying to get in. Manage participants. Becky is not asking to come in. So, starting off with what we do know is we know that 1 electron. 1 electron is how do I clear all drawings? Okay, so 1 electron or one proton has, and for electron it's negative 1.6 times 10 to the negative 19 coulombs of charge. This is the set quantity that you have for a electron. Oh, why didn't that go negative? Why didn't that come up as a negative? Control Z. Negative 1.6 times 10 to the negative 19 coulombs of charge. So that's one value that we need to remember. The other thing that I want you to remember is that when you have an electric field, which direction does the electric field go in? Does it go from, why is this coming out as green? Does it go from positive to negative or negative to positive? Any takers?
Positive to negative.
Negative
Sorry?
to positive.
Negative to positive or positive to negative?
Positive
Depend-
to negative.
Well, it depends how you see it, right? It's all in perspective, right?
What do you mean how you see it?
Right?
Well, it's arbitrary, I'll give you that.
Does it
What
not
is-
matter?
So this is, well, no, not really. As long as you have the same, the same standard worldwide, I don't think it would matter. If it was the other way around worldwide, we just have that as our convention. When Benjamin, this is Benjamin Franklin. He had a 50% chance of getting this the way it was. And if he got it this way, electrons would be positively charged and protons would be negatively charged. But he got it the other way around. So we have a convention, and convention just means something that people just agree on, where this is the way we draw how electricity flows. So electricity always flows from the positive. It's always coming from a positive source. If we have a point charge like this, you will have the charge radiate outwards from that positive point charge. Let me just give that a positive value there. So we have a positive charge there. From that positive charge, you will get positive field lines, and they will radiate directly outwards from the object. Now, if I was to draw a convention like this with field lines like that, and then I was to draw a smaller charge, if I was to draw a smaller charge there and also make it positive, how would, by convention, oh goodness, that's tiny. How would, by convention, I draw the field lines?
They would be all sort of going out from a little ball, but then going in towards the other one.
No. Assume that these two objects are far away from each other. They're not interacting. I'll erase this one. No, I want to erase it just because I want to keep it there for comparison. If these are separate, if these two are separate, how would you draw the field lines on it?
Connecting?
Let's say that this one here, goodness gracious me. Let's say this one here is 10, the charge is 10 times greater in this one. If it's 10 times greater, what would happen to the field lines?
They would be longer.
Would they still radiate outwards? Tim, what do you think? Would the field line still be going outwards?
Maybe yes.
Okay. If the convention states that field lines always go out from a positive source, then they're always going to go out. However, if I have a smaller charge, much less charge, what's going to be the strength of that field? Hajin?
Yeah.
So what would be the strength of the smaller point charge? If the charge is smaller, the strength of the field will be larger or smaller?
Chris, smaller.
Sorry, what was that?
Smaller.
Smaller, great. How do I show that, Hanbi? Hanbi?
Yeah.
Yep. How would I show that the field lines are smaller or the force is small?
I don't really know.
Okay. GA, what do you think?
I don't know.
Quick question.
Yeah. Let me.
Can't you just draw the same thing but smaller?
Dylan, thank you.
No, because you're like just make it smaller and literally.
Yes, of course, that's what you do. You just have smaller field lines. If it's a smaller charge, the field lines are smaller. Because there's less energy in the per unit of field line. So this is a concept called a vector. Have you heard of a vector before?
No.
So
Direction
field
and
lines are a
magnitude.
type of vector. Now vectors are different from scalar quantities. So if I say someone weighs 12 kilograms, there's sorry, nobody weighs 12 kilograms. Let's say if an object weighs 12 kilograms, it doesn't matter which direction it's traveling in. It's still going to be 12 kilograms. So that's a scalar quantity. It doesn't matter about which direction it goes. But some things do matter about direction. So when you remember doing your unit on forces and Newtonian motion, Newton's 3 laws of motion, there was always a direction involved, whether it be up, down, left, right, or a combination of these directions. Well, field lines are the same thing. They have a value. There will be a certain strength in the field, but there's also a direction. Vectors have magnitude and direction. If you can't remember this, you need to watch Despicable Me again. You remember that? The guy that's
Vector.
like an evil Bill Gates.
How's it magnitude though?
Pardon?
How's it magnitude?
So how strong it is. If I have if I have this as the power in a lightning bolt of say 15 coulombs, you better believe that the electrical field around it is going to be high as well.
Okay, sir.
If you had something that was just one electron, what would be the magnitude of the electric field around it?
1?
1,000?
Really small. I don't know if it's I'm not sure how. Let's just check. How do you measure? What is the measurement of an electric field? How do you measure an electric field? What unit do you have it in? I think.
What are vectors?
Vectors are things that have a value, like a numerical value, and a direction. So if I say 15 kilometers an hour, there is a direction that it's involved, that's related to it.
What? Wouldn't it be if you said 15 kilometers an hour north?
Yes, well, maybe. Normally you have X, Y, and Z directions, and then you do a combination of the whole three of somehow. But there's always a direction involved with it. Same with magnetic field, with electrical field lines, there's always a direction involved. Was that clear, Billy?
Kind of. I mean, I don't see how something can be just going, say, something travels at however many kilometers an hour, but you're not saying which direction you're going in.
It's normally relative to a reference point. So if I'm standing still and a car is driving away from me, then it's accelerating away from me. So it has its direction is away from me. However, if I'm standing still and the car is coming towards me at high speeds, then the acceleration is towards me. So there's a direction involved. It might be coming towards me at 60 kilometers an hour. It might be going away from me at 60 kilometers an hour. But one of those two is going to cause me concern and one will not.
Blue shift.
You remember that, do you? Great.
And redshift. The
Okay.
times.
Let's see how we can work out how to measure one of these fields. So it's actually really difficult to measure these fields directly. I mean, you could do it, there is a formula called Coulomb's law, which is in last chapter. You could use Coulomb's law where you have the force equal to Coulomb's constant, which is 9 times 10 to the 9 newtons per coulomb, and then you multiply that by the charge. If it's the same charge as the charge squared, and then you divide it by the distance squared, the distance between the two charges squared. So electrical fields don't really do anything to something that is not electrically charged. So if I put in a neutral atom into an electric field, one that has all its electrons and all its protons there, nothing will happen to it. The reason why nothing will happen to it is because it's electrically neutral. You have to have two objects in that field. If we went down to this here, what you would end up doing is you could see that these are both positively charged. Can I do a, yeah, okay. So if this field line is going this way and this field line is going this way, one is going to get pushed aside because opposites do not attract. What will probably happen is that this field line will push towards until it gets close enough that it'll start doing that.
Can it like reflect back?
Yeah, but field lines can never cross. So you'll have these field lines go out and then they'll kind of move aside almost. Is there an example picture where you can see this? I think you can see this in page, yeah, on page 520, you can see these field lines going away from each other. So you have two similarly charged particles over here. That one there, page 520. So they're repulsed from each other. These ones are attracted. So you can see that the field lines are not directly radiating outwards. They go in towards each other. So one of these will be positive, one of these will be negative. Let's actually assume that that top, can I take a picture of this? No, maybe I'll try online. Okay.
Mr. Andrew,
Yep.
right in the middle and between them, I don't know if you see it, but there's a little section in between the two dots that looks like a part inside the circle.
Looks like the what? Yeah, there's a sort of a spot where there's not a lot of force going either way. The field lines aren't going to be having a lot of effect on anything. Okay, so after that, what do you want to look at? We want to look at the potential energy. That's the bit that we need to look at. So I said yesterday, if it worked, what you had was you have potential energy in an object depending on its location. So the further something is away from planet Earth, the more potential energy it has in reference to Earth. So the moon has a lot more potential energy. If it came crashing in towards Earth, it would have a lot more potential energy than if it was already here, balanced on the surface of the Earth. That doesn't actually make a good example. If something falls from a higher position, it has more potential energy. If a bow is pulled back more, it has more potential energy. If in an electric field, the electron, because that's what's normally moving, if the electron has to move further across a field, that potential energy that it can build up then as it comes out the other end is much, much higher. It's one of the principles that the old cathode ray tubes were functioning on. Anyway, let's work out how we can figure out. I'm going to get rid of the. Do you want me to leave Coulomb's law up there for later? Anyone? Is anybody still there?
Do we even need to? know
Do you need
that?
it?
I don't think you need it.
Okay, then no.
It is the basis for working out potential energy. Does anybody remember what the rule? What the equation for potential energy was? What happened to my? Wait. Where's my?
Wasn't it different for elastic and the other ones and all like that? Like,
Second, I've lost my whiteboard. Okay. There we go. That's what I want. Can anybody find me how to work out potential energy?
Isn't it? Oh my gosh! Isn't it mass times gravity times height?
Yes, kind of. The potential energy is that's when you're really close to one edge of that field, being the Earth's surface. That doesn't apply when you're in the International Space Station. That's only a few kilometers above the Earth's surface. It's not that far away. So you've already lost most of the effects of gravity when you get that far out. Although there is a centripetal motion. Centripetal motion as well, so that kind of cancels it. All right, let's try and show how potential energy can be calculated in an electric field. So your potential energy is equal to that Coulomb constant that you can see there again. And we're only going to look at one of these. So you have we assume that one of the charges has to be small, so we give it that little q. That little q is the test charge, so it will be maybe 1 electron. Now remember that this electron still has an electric field associated with it, so it will also influence the larger plates that normally they're plates that have a big charge q. So you can charge these things up twice. Then it is only relevant to the distance that the charge has to travel. So it's that position of the one charge in a field. So it's not d squared. That's got to do with the force in between them. But the potential energy has to do with the distance. Why?
Less distance, more power.
What's the unit for energy?
Joule.
There you go. What's the definition there?
Of joule.
Yeah. But if you have energy, it's something. Joule has a bunch of units attached to it as well.
Okay.
What does a joule represent?
A unit of work or energy.
Or a
I don't know, object?
Force factor?
I just typed it in behind the J.
What's a NM?
What's the unit of force?
Newton meter?
That's it. So if you
Sold to the black guy.
So if force has to do with newtons and energy has to do with Newton meters or joules here, can you see how this equation has been modified to be able to, the force equation has been modified here to be able to figure out your potential energy?
Wait, those are both same or different?
Pardon?
Are they both same? What do you mean modified?
No. So potential energy equals force over, force times distance, okay? Okay, so if this is force times distance, you've lost the 1d underneath here.
Mm-hmm.
You've lost the distance between them by 1, and that's gone up over here.
Okay, so it's F times D.
Yes. Remember that this Coulomb's law is so similar to gravity. It is so similar except that we don't really see it unless we're really, we only really measure it when we're at Earth's surface. So we don't see that it's our gravitational pull and the Earth's gravitational pull multiplied by a gravitational constant divided by the square of the distance between us. We don't see that happen, and we simplify the equation to mass times the gravitational constant at the Earth's surface. So mass times gravitational acceleration by height is a simplification. Just the same way that this is a simplification. Just the same way that this is also, this is not as simplified. We might be able to simplify that. Oh, we might be able to simplify that, but we're going to be working with a concept of not just electrical potential energy, but electric potential. So when you have electrical potential energy, this will be measured in joules, okay? But electric potential is measured in volts. And the definition of electric potential, it's equal to
Electric potential energy divided by charge.
Divided by charge. Or by Q, I should say. Okay? So to get that division by a charge, which charge do you get rid of? You get rid of the test charge. So you take this potential energy equation, and then you have your electric potential will be equal to KQ divided by D. That's your equation. This value here for K equals 9 by 10 to the 9, is it? It's Coulomb's constant. What is Coulomb's constant? Coulomb constant. The value of Coulomb's constant is kilograms using ampere squared. Okay. So you don't really need to remember the unit for this. You don't really need to remember the unit, but just know that there is a unit there. There's a number that pops in here. So your volts is equal to your coulombs divided by your distance times 9 times 10 to the negative what? Negative? Whoa, no, it's positive. 9 times 10 to the 9. Now this is just a constant. It is, but it does help you work it out later if you need to. I'm just going to get rid of this so it doesn't confuse you. Okay?
That thing is to the power of 9, right?
Yes.
Okay,
So if I was to have, and I want you guys to try working this out before we go today, that's going to be the end of this. I'm going to get rid of the stuff on this side of these, or do I? I will get rid of, where's the eraser? I'm going to get rid of that, and that. Okay, so I'm going to put into this electrical field between these two charges, I'm going to drop a little charge here, okay? I've got a little positively charged particle in there. I'm going to give it a positive charge so we don't get it confused. Wow. Okay, so there's a little positive charged particle going to move there. There's going to be a distance between these two. Let's give that a distance of Let's go 1 centimeter. Let's go the distance of 1 centimeter. And let's give it a voltage of, let's say that the electrical potential of this system, if you had this jumping between this, not 1 centimeter. What am I talking about? That's 10 millimeters. Yeah, okay. Let's give it a voltage of, a system with
200 volts.
no 1,000 volts.
Okay.
I won't say V, I'll say electrical potential. Okay, my question. How much charge is on that positive particle?
1,000. Am I wrong?
Who else do I have? Jonathan, what do you think?
And then hear the question, sorry.
I have a small charged particle, positively charged particle in an electric field. The electric field is 1 centimeter. I'm going to move it 1 centimeter. It's going to move 1 centimeter until it stops at the negatively charged spot. The electric potential of this field is 1,000 volts. What is the charge on this little thing?
1,000.
100 maybe?
You can work it out, you know.
Wait, no. I'm trying to remember the numbers you said.
Okay. So we have this electric potential equals 9 times 10 to the 9 Q.
Joe,
What happened?
so like 1,000. So the book says 1,000 volts is 1 coulomb.
Not necessarily. 9 times 10 to the 9 is your Coulomb's constant, and we don't know what the Q value is at the moment. We do know the distance that it's going to be traveling, which is 1 centimeter. And since we work in meters here, it's 0.01 meters. Okay? When you've got that, and I know that my voltage is 1,000, can I work out? Can I
Yeah,
work
you
out
can.
what the charge is?
I thought you were trying to find charge. C, right? Is C
No, your
Q?
charge is Q.
Oh, okay. For this one, what formula did you use?
I really hope I'm correct here. Am I doing this the wrong way? It seems to be the wrong way. But we should be trying to work out the amount of joules that's involved here. This doesn't seem right. Oh, I know what the problem is. Sorry, this is the question. This is the way that people would do it in the This is the way we do it in physics. I'm so sorry. So what we are actually going to be working out is we won't be giving you that. What we will give you, sorry, that's too difficult. The electrical potential will give you, let's say the electrical potential is still 1,000 volts, but we will tell you what the energy of the field is. So we'll give you the field in joules. We'll give you the field energy in joules. So the positive object in there, that will give you the positive object in there of, I want to get it, let's say it's going to be around 3 times 10 to the negative 16. How do I have the, no, 16 doesn't sound enough either. Negative 12 coulombs. Okay.
That's supposed to be. Oh wait, we're looking for the joules.
Yeah. So very, very simply, the what you're going to be looking at is volts equals 1 joule per coulomb. That's what they're looking for. That's what they're looking for in the textbook.
I have a question.
Yeah.
How do you get this?
I'm just giving, this is your this is the task that I'm giving you. I want you to field energy in joules is what? Question mark. What is the field energy?
1,000 joules.
What's field energy like in like? Is it F? Is it K? Is it Q? Is it D?
No, it's in joules.
So J.
I'll make it easier.
Wait, hold up. So the joules is equals to EP times C, right? And this is the C.
Yep.
This is the EP. So you just times this together.
Yes.
Equals joule. Yeah, look at that.
Yeah, but what's the value?
Okay, let me just work out the math.
You look at my answer.
How do you write this in the how do you hold up? How do you write this in the calculator? It's not possible. Hold up.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then you have the 3 there. And then you want to multiply that by 1,000. Actually, you don't even need to do that. So if you're multiplying them both together, you know that 1,000 there is 10 to the 3. So 10 to the 3 over there would just mean that your amount of joules would be equal to 3 times 10 to the 9, -9.
1, 2, 3. Yeah. 9 plus 3.
3 times 10 to the -9 joules.
Yes. Yep.
Does that make sense?
Yes. So we should. What's K again?
K is 9 times 10 to the 9. It's the
Oh, okay. And what is this?
Sorry?
What is this?
What are you pointing at? Oh,
This-
that's Coulomb's constant. It's a constant that just allows you to convert between the units.
Do we need to memorize this so we know the EP?
No. In fact, the only thing that you really need to memorize, this is the most important thing. Memorize that. I'll make it. This is what you want to memorize. Make sure that this is memorized very, very well. 1 volt equals 1 joule over 1 coulomb. In fact, if you want to practice this and make sure they work, questions 31 and 32 in your textbook are good examples of what you will get on the test.
So if it's 2 volts, it's 2 joule over 2 coulomb, right?
No, 2 volts would be 2 joules over 1 coulomb.
So it's always 1 coulomb.
Not necessarily. I mean, 2 volts could also be 1 joule over half a coulomb. Or
So
2
confused
volts
right now.
could be 200 joules over 10 microcoulombs.
So confused. Okay. How do you find volts then?
How do you find volts? Okay, so for example, if you do 10 joules of work. Yep. Yes, thank you, darling. So, for example, if I was to have, let me make this bigger. If I was to have an object that was very positively charged, and then I take another object and it's also positively charged, and I start pushing it into that field, I'm doing work. I am giving this thing potential energy by pushing this into the field. If I let it go, what's going to happen to this positive? If this can't move, what's going to happen to this positively charged object that I let go of?
This is flame. Just move away.
Gonna fly away.
Exactly. And I can work out. I can work out from the amount of energy I needed to push it in, that's the joules, and the charge of this, what is the potential difference between these two objects?
Thing over thing. Yes, okay.
Okay, do you think we need to go over this? Do you think we need to go over this next week?
What about tomorrow?
I am getting wet.
Oh God. What about tomorrow? What do we do?
Oh, goodness. I love Indonesia. But
For tomorrow, are we just gonna do the... Okay, bye.
have a look at that.
CJ says they're having fun.
Bamboo is nearly... dude, there's bamboo coming into my backyard.
You should get your kids inside the house.
Yeah, I think I'm actually going to take my power supply out from outside before it gets electrocuted.
All right, goodbye.
I'd say that we'll go over these sort of problems next week.
Okay.
Tomorrow I want to have a look at the assignment that we've got, okay?
Mm-hmm.
Okay.
Sayonara.
Sayonara, guys.
Bye.